Okay, I'm very excited. I'm very excited about today's lecture because it's a fantastic topic, really amazing topic, one of the wonders of this world. Okay, so this will be a lecture on thermodynamics and the relation between micro and macro science, physics. Okay, and that's the first time that we are in this course, we are going to discuss seriously the relation between microdynamics, microphysics, and the physics on the macro scale. Particularly, as the title that I put here indicates, the notion of irreversibility, namely in the micro, we discuss that the fundamental forces are micro-reversible. There is no specific favor direction, so to speak. But that is going to change in a very dramatic way when you go to macroscopic systems, and this is what thermodynamics is telling us. Okay, so what I'll do here, I'll discuss briefly a few of the fundamental laws of thermodynamics. Then I'll spend considerable time to discuss the origin of the macro-irreversibility according to Boltzmann. And this will lead us to a question about error of time. Does thermodynamics provide reason why we feel the past is so different from, we perceive the past so different from the future, and causality, etc., all the topics that we discussed until now. And then I'll conclude by what's known in modern philosophy of physics as the past hypothesis, and we'll discuss it at the end of my lecture. All right, so thermodynamics is a very foreign theory. Most of us study in high school Newtonian equations, forces, momenta, velocities, acceleration. We're familiar with that also intuitively. But actually thermodynamics is kind of weird because all the ontology, all the descriptions are going to be different. We're not going to talk about particles, we're not going to talk about position of the particles, we're not going to talk about velocity, we're going to talk about other beasts, okay? Amazingly, that's one of the amazing stories of thermodynamics. Amazingly, thermodynamics was developed before the kinetic theory of matter was developed. So when thermodynamics was developed as a theory in physics, experimental and theoretical, they didn't even know that matter consists of molecules or atoms or ions or particles, microscopic, that move around and so on. The kinetic theory of gases or the atomic theory of matter or whatever. So it's amazing that one could develop such a beautiful macroscopic theory without any idea about what is supporting it on a microscopic level. But today, of course, it's very different. We know how to relate the macro and the micro in some sense, okay? So today it will not be so mysterious, and we will leverage this as we'll go forward. Okay, so let me just, okay, so here it is. Okay, so I want to, so macroscopic system, by that I mean system which is large, which the number of degrees of freedom is large. So think about a mechanical system, a gas, a solid, a fluid, consisting of many particles, and mathematically it will be the limit of infinite number of particles, but this limit doesn't, we don't have to be so rigorous and precise mathematically at this point. A macroscopic system of macroscopic scale, okay? How do we describe it? So we describe it in terms of macro state. Thermodynamics is about the macro state of a macroscopic system, Okay, so macro state is not interested in the details of where each atom is and what is its velocity and so on, but a more macroscopic characterization of the state of the system. Now, so the macro states are defined by macro variables, variables which are macroscopic, which are properties of the macroscopic system. For instance, a volume, number of particles. Volume makes sense only if we're talking about fluids or gases where the volume can change rather than a piece of solid. But okay, number of particles, pressure, energy, temperature, entropy. If the system has magnetic properties or magnetization, and so on and so forth. So these are all macro variables. So the list of macro variables are, some of them are kind of universal, the number of particles, energy, temperature, entropy. Some of them are more specific, like pressure, again, and volume is for gases or fluids. Magnetization is for system that have magnetic properties, and so on and so forth. So there is no strict list of macro variables. Some of them are really universal, and some of them depend on the situation. Okay. An important example of a macro variable, which is somewhat counterintuitive, and this is the density of matter. So if you talk about global density, simply N over V, the number of particles divided by the volume of the system. But what I mean is density profile. Density profile means the number of particles per volume at a particular location in space. Okay, so how many particles, how many molecules, or how many atoms, or how many whatever particles occupy a given location in space. So this is a profile. This is a function of X. This will be a row of X. I had row there. I don't know, it disappeared, but anyway, okay? So it's a three-dimensional profile, the distribution of matter in space. And similarly, you can do the number of particles per unit volume in velocity space. And then it will be rho of V. It will be the distribution of the velocities. How many particles per unit volume of velocity have a certain velocity, and so on and so forth. So these are already, you think that they are microscopic, but they're not really microscopic, because a given, I'm not specifying which molecule has a given velocity. I'm just saying how many molecules have a certain velocity, or how many molecules are in a given location in space. Okay, so that's again, it's a macro variable, macro characterization of the macroscopic system, but it has some spatial locality. Okay, so these are macro variables, and specifying a value for the relevant macro variables defines the macro state. Okay, you change the macro variables, you get into different macro state of the system. Okay, two more terminology items. What systems are we talking about? We're talking about two types of systems. One is isolated system, a system where particles do not leave or enter from the environment. So the system doesn't exchange particles. So N is fixed and doesn't change. And also there is no exchange of energy. So the system is really isolated completely. There is no interaction with the environments whatsoever. Closed system is somewhat weaker notion. Particles don't leave or enter into the system, but the system is able to exchange energy with the environment. For instance, you can imagine that you then you apply external force to compress the, the, the gas, okay? So that will be interaction, exchange of energy with the environment, or that the system is cooled by the environment or heated by the environment. So that's the notion. We will talk about closed system interacting with the environment in two ways. One is applying forces on the environment or from the environment on the system. And another one is interaction with the heat bath. In other words, that the system is embedded in a heat bath. Heat bath is an idealized notion of a system that is so huge that whatever is our little closed system is doing, the temperature of the heat bath doesn't change, but it's quite a reservoir of energy or heat that can go back and forth with our system. Okay, again, I'm popularizing things, but it's good enough for us. Okay, so let me, okay. So I'll come back to this example, to particular example, it will be clear. The most important macro state of a system is what's known the equilibrium state. The equilibrium state is a macro state that doesn't change with time. So when the system evolves in time in general, when the microsystem evolves in time, obeys Newtonian mechanics and there are forces or whatever, then of course it may be that the macro state also will change in time. Okay, so in general, macro state is not will change in time in general, but equilibrium is what happens when the macro state is reaching a fixed macro state. Okay, it doesn't change anymore. So it doesn't mean that the particles don't move. If it's a gas or whatever it is, the microscopic particles will move. So there is still a trajectory in phase space, as we'll see, but the macroscopic state don't change anymore. So then this is what's known as thermodynamic equilibrium, and that's equilibrium state. It's extremely important because many of the interesting properties of systems, of matter, and so on can be derived from approximately an equilibrium state. In equilibrium, there are laws, thermodynamic relations between the different variables, the macro variables. So that they are called equations of state. And here are two which are kind of very popular, classic in ideal gas, which is the same thing which we'll talk again and again today, because the simplest model is you have a container with a gas particles. Okay, so ideal gas means that they are very weakly interacting. So they're basically interacting when they collide and go off each other, but otherwise they're not interacting. It's called ideal gas. And here are two examples of equations of states. One of them is relating pressure, volume, number of particles, and temperature. PV equals to NKT, the famous equation of state. K here is a constant, it's Boltzmann constant. It's not a variable, just a constant. It has units and so on. Boltzmann constant, we can ignore it, okay? And the other equation of state is relating the energy of the system to, again, number of particles and temperature. And it's 3/2 NKT. The 3/2 is an ideal gas because they are very, almost you can ignore the interaction between the particles in the gas. So all the energy is the kinetic energy. So, and there are 3 dimensions. So each particle, so this is why there is a factor of n. And as maybe we'll see at the end, the average kinetic energy in a given temperature in ideal gas of each particle is 1/2 kT. Okay, and because there are three degrees of freedom for each particle, Vx, Vy, Vz, then this is a factor of 3. So that's a very well-known relation between energy in ideal gas and temperature. In some popular literature, or maybe even not popular, they'll say temperature is defined as the mean energy, but it's not. This is specific to to ideal gas. Okay. The more general definition of temperature is a more abstract. It is a quantity of a system such that when two systems have T1 and T2, then if you put them together they're able to exchange heat, then they will equilibrate and will have a temperature in between. If the same sizes, then it will be in the middle. If it's not, whatever. But so differences in temperature of two systems is telling you how far they are in equilibrium with respect to each other, how far they are not in equilibrium. So if you allow two systems to exchange heat, then eventually they will reach an equilibrium for the entire system in which the temperature will be the same. Okay. An example of equation of state in a paramagnet is number of particles, the magnetization number of particles times the external magnetic field with some constant, which is the susceptibility, and doesn't matter what it is. Okay, so that's examples of equations of state. All right, so this is kind of how thermodynamics look like. First of all, equations. First of all, equilibrium. These are the macro variables. There are relations between them, and so on. All right. So another important notion, extremely important to the whole discussion today, is the notion of reversible and irreversible processes. So I'll take colloquially, irreversible process is a process that evolves spontaneously. So now we're talking about dynamics. Okay, irreversible process is the process by which a system that is initially in a non-equilibrium macro state evolves in time and reaches the equilibrium macro state, right? And then, of course, once it's in equilibrium, nothing changed. So the macro state remains fixed. So this is the irreversible process, a spontaneous evolution of a macro system, a macro state from non-equilibrium to equilibrium. Reversible process is a process in which the macro state changes, but changes in very adiabatically, very slowly, in such a way that at any given time, the system is in an equilibrium. So you go from one equilibrium to another, but by a very controlled manner. And the distinction between the two will be important. So here are the classical examples. Again, we're talking about container of gas, ideal gas. You start with an ideal gas, with a gas in the left chamber. So imagine you have the container and you have a partition. And initially, all the gas is constrained to be in the left chamber, and the right one is vacuum. So it has some equilibrium. It has some pressure. It has some temperature. It has some volume. It is the equilibrium of that configuration. But now imagine you punch a hole or you lift the partition, and then spontaneously the gas will move, leak through the hole, and gradually fill up the entire container. And then you will reach a new equilibrium where basically the system, the two parts are exchanging molecules and energy, and you will get some new pressure, new volume, and the same temperature. Okay, why the same temperature? This is an example of irreversible, the top one, irreversible process, and I'm assuming in the top one that the system is isolated. So if the system is isolated, conservation of energy says that the energy will not change, okay? And therefore, if the energy doesn't change in this ideal gas, I remind you that temperature is fixed by the energy. So if there is a conservation of energy, and I'm assuming that the top one is isolated, okay, then the energy doesn't change, and therefore the temperature at the new equilibrium will be the same as the old equilibrium, but different pressure and different volume. Volume is larger, pressure will be smaller by the same amount. Okay, again, from PV equals to NT. So it's very simple. Okay, that's an irreversible process. Now we can imagine going from the initial state to the final state, but in a different route. In this case, in the bottom one, I'm assuming that the system is closed, the chamber is closed, but it is interacting with the environment. It's not isolated. In both ways. First of all, there is a work that can be done on the system, or the system can do work on the external world. And also there is an exchange of heat between the heat bath and the system itself. Okay, so now in this scenario, the partition is basically a piston, and there is some weight here, and the weight is basically putting pressure on the piston opposite to the pressure that the gas. So it's almost like nothing changes, but little bit weaker, so allowing the piston to move little bit upward or to the right, doesn't matter. And now eventually, by a slow process, the final system will be basically the same as before, as the one in the irreversible process, because I'm assuming here that the process, the reversible process, is such that it's isothermal. Isothermal means that I'm keeping the system always at the same temperature. And what does it mean? So imagine now the system is expanded. If it's expanded, it will cool. But in order for the system to be at the same temperature, while the system expands slowly, it gets heat from the environment to compensate for the expansion. And this way, the temperature remains the same. So the final state in both scenarios are the same, but it's different. In one case, it's isolated system in a spontaneous expansion, irreversible. In the second one, it is a closed system, not isolated, and it is a reversible isothermal expansion that every state, its system is almost at equilibrium and so on. Why do I call the first one irreversible and the second one reversible? I just said this one is kind of spontaneous and the other one is controlled, but the reason is very simple. Suppose I want now to take the bottom scenario and to bring it back to the initial macro state. Okay, so that's very simple. What I do is put the pressure, again, weight on the final configuration, and slowly put the pressure, slowly compressing it. Again, the system now, because it's compressed, will exchange heat to the environment in order to keep the same temperature. And eventually I'll come back to the initial configuration. That's the reversible one. I can do the same for the top one. I can say, I want the top one to go back to the initial one. Okay, I cannot do it with the isolated system, of course. I can do it in the same scenario. I can say, well, now let me put a pump to compress it and let the heat exchange so that it will keep the same. So starting from the final states, in both cases, I can compress it in kind of an adiabatic way if I'm allowing in both cases exchange with the environment. Okay, but in one case, I claim in both cases, our system will go back to the same state. So why do I call the bottom one reversible and the top one irreversible? The reason is that if I, in the top scenario, when I'm compressing it back to the initial state, the world has changed. In the bottom one, the world, when I complete the cycle, the world itself got back to the same position. Okay, so let me explain what is it. So this is the first law of thermodynamics. It says conservation of energy. It says if you have two equilibrium states, like initial equilibrium state and final equilibrium state, then there is a difference in the energy of the system, which can come from two sources. Delta W is the work, possibly work that the environment does on the system, like compressing the system by some pump. And delta Q is the amount of heat that is leaking to the environment. So this is why delta Q minus delta W is the delta E. So that's basically conservation of energy. If there is a change in the energy of the system, it must be the sum of the two, okay? There is an interesting introduction of entropy here. The entropy is related to the change in the heat, okay? So unlike work, unlike energy, unlike temperature, unlike entropy, heat is not a property of the state. Heat a property of the process in which I went from one state to another. Delta S, entropy, is a property of the state. And it's defined the following. Suppose I'm starting from some equilibrium state to another equilibrium state, okay? I can now ask, if I went from one state to another through a reversible isothermal process, then the difference in entropy is delta Q over T, okay? But again, that's defined delta S, okay? So the difference in entropy is basically the difference in the heat, in the amount of heat which is exchanged going from state A and B, but it's defined to be specifically the amount of heat that has been exchanged between the system and the environment if you did it in an irreversible way. So let me explain, going back to here, okay? So in the first one, in the isolated case, delta Q is zero. There is nothing in the environment. Delta Q is zero, delta W is zero, the energy is of course the same, the temperature is the same, but also there was no change, there was no work applied, and there was no exchange of heat because it's completely isolated. Okay. What happens to the entropy? Well, at this point, I don't know. To determine whether there is a change in the entropy and what is the change in the entropy between the final state and the initial state, I have now to ask what happens if I go from the initial state to the final state by a reversible process. Okay, so now I'm imagining the scenario at the bottom. And here we know what happens. Delta Q, the system during the expansion, the system absorbs exchange heat, which is exactly the same amount as the work that the system is doing on the pump, on the piston, delta Q equals delta W, and therefore there is change in entropy. The entropy increased because there is a heat which is entering to the system. Entering the heat means changing the entropy, okay? But because of that, I know that also in the top case, the entropy has changed, although the delta Q is zero, right? Because the entropy doesn't care how you went from A to B. Then if through a reversible route, there was a change in heat, exchange of heat, then it means that the final state has a larger entropy from the initial state, if there is absorption of heat. If there is a leak of heat, then delta S will be negative. So this is why I know that delta S in the irreversible case is bigger than zero. Okay, so now why this is reversible, irreversible, you can see here. Okay, so imagine in the, I'm sorry, not here. Okay, here. Imagine now that I'm compressing in the two cases the gas back into the initial state. Okay, so in the first case, what will happen, I'll have to allow the system to have a work done on it and to allow the system to leak heat to the environment. And then eventually I'll get to this chamber. So in the second part, in the compressing part, there is delta W, work done on a system, and this work was completely, fully converted into heat, okay? So the system itself, the system that we're talking, the gas, okay, came back to the same state, macro state, but the world has changed, right? Because now there is a network that has been done and converted into heat, work converted into heat, so the world has changed. As opposed to the reversible case, if the expansion was reversible, and then I reverse it and compress, then now instead of delta W that the gas has applied on the piston, now the piston, the pump, is applying the work back onto the system. And the heat that was entered into the system from the environment is now leaking back to the environment. So when you go back, not only our system went back to the same state, but also the world. Okay, so you basically didn't do anything. So you meant the cycle, nothing has changed after, at the end. There is no net change. This is why a reversible process is reversible, because you can reverse it from A to B, you can go back from B to A, and neither your system, of course, because you went back to A, but also the world has not changed. So that's good. Okay, so now to the main thing, the second law of thermodynamics. So you already see here, I hope, that in this spontaneous free expansion, the volume increased. Now the gas is filling the entire volume, and there is an increase in entropy. And in both cases, it doesn't matter. Also in the reversible one, now the gas fills the entire container volume, and there is an increase in entropy. Okay, so now the question is this a specific case, or this is the rule? And then the fundamental second law of thermodynamics said that there is no physical process by which the entropy of an isolated system decreases. So the fact that the top one, which is isolated system, during this expansion, or as a consequence of this expansion, the entropy increased, is no accident. This is a universal fundamental law of nature. If the process is irreversible, delta S must be bigger than 0. If the process is reversible, delta S is 0. Okay? So this is amazing, because now, before we understand where it's coming from, but now we understand what is equilibrium state, or what is irreversible. I said irreversible is the taking a system and let it spontaneously evolve into the equilibrium state. But now we know what it does. The system basically starts from a low entropy and evolves spontaneously to eventually to the maximum entropy that is allowed. In other words, this uniform density of the gas in the container is the maximum entropy that is allowed by the constraint of the container, the new constraint on the container, right? So irreversible process is the evolution of the system to maximize the entropy. Maximum entropy principle is so fundamental and appears in many contexts. All right, so now let's go back to this. So here, in both cases, delta S is bigger than 0, right? But I just said that in a reversible case, delta S is is zero. So what is the answer to that? Again, here I said, in a irreversible case, there is increase in entropy. In a reversible process, there is no net change of entropy. In this case, both of them have, in both cases, right? It doesn't matter how you do it. Delta S is delta S, right? Delta S is a property of the two states. I don't care how you got it, okay? So what is the answer?
Second system.
Basic physics. What?
The second system isn't isolated.
Right. It's a very important and sometimes ignored that the second law is about an isolated system. And so many garbage and BS is in the literature. Philosophers, scientists, biologists completely mix the thing. You know, how come life is against the second law of thermodynamics? They forgot that it's not about, that the second law is about isolated system. So let's go back to this, our system, and see if it works. So I put the environment now, okay? So in the case of the irreversible, there is no interaction in the environment, with the environment doesn't change anything. So delta Q is zero, delta W is zero, delta S is zero for the environment. And our container is isolated. And of course, delta S, as I said, is bigger than zero, according to the second law of thermodynamics. In the bottom one, if in order to talk about isolated system, I have to put also the environment inside this isolated system. And now we see that indeed there is no change in the entropy because there is an increase in the entropy in the container itself, but the work delta W on the environment is of course minus, and the same is the heat now is minus, and therefore there is a net decrease in the entropy during in this expansion in the environment, and therefore the total entropy doesn't change. So when you expand reversibly the gas, okay, you increase the entropy of the gas because now it fills this entire volume and so on. There was absorption of heat, but the same amount of entropy was lost in the environment. The environment lost entropy or decreased entropy, but it's exactly the same amount. Okay, so the second law of thermodynamics is about isolated system. And therefore, don't start to think about, you know, how come a living system is doing. Living system is a low entropy, and we'll come to it, but it's not an isolated system. And we'll come back to it soon. All right? Okay, questions so far? Shane. Hi. Everything is fine?
Yes.
Good. All right. So now we are going to ask the most obvious question. How come we have now an error of time, the first time in our exploration of physics, that there is a law, fundamental law. It's amazing law because it's in all, it's so universal. It doesn't matter, you know, if it's cosmos, if it is you know, black hole, if it is galaxy, if it is small container, whatever, if it is fields, if it's photons, if it's whatever, second law is engraved in stone, not only in the textbooks. But we don't understand where it's coming from. How come you have a how come you have macro-irreversibility in the sense that there is now error of time, right? That delta S necessarily bigger than zero, which means that there is a preferred direction of time. And that's amazing, right? Where it's coming from, okay? So let's then go back to here, to our gas, okay? So imagine now that we take snapshot of the gas. Okay, so it starts, you know, after we took out the partition. So this is the A, the initial state after the partition was removed. And then halfway through, you know, the gas starts to fill in, and then eventually it goes to kind of uniform filling up the entire chamber. Okay? Now, the point is that sorry. This is my confusion. Okay, what I meant here is to change the order, and I forgot to do it, you see. Okay, so I am micro-reversible. So what I mean, but not this one, sorry for that, is we don't see the reverse sequence. We don't see D goes to C, goes to B, goes to A. And the question is why, okay? Why don't we see the reverse sequence? Okay, we can, to be even more specific, imagine I take the state D, which uniformly fills the entire chamber, and I reverse the velocities at some time. I reverse the velocities of all the particles in the uniform chamber. If the Newtonian dynamics is not violated, then I should see precisely D goes to C, goes to B, goes to A. I should see kind of spontaneous compression, because this is precisely what micro-reversibility says. Reversing the velocities will give you the trajectory, which in terms of X will be just the same as the forward. The velocities will be reversed, okay? So that's the question, why the sequence, which is increasing the entropy, as we discussed, by filling up the entire chamber, is something which is expected by the second law of thermodynamics, while the sequence where you go from high entropy to the low entropy state by reversing the velocities is something that never happens, or at least is not only never happens, it's sanctioned by, it's illegal according to the second law of thermodynamics. It says no, that's not allowed, because this will be a spontaneous compression, a spontaneous process that that decreases the entropy. Okay, that's the fundamental question which I want to discuss. Is the question clear? Okay, so what I'm going to say up front, that we are not going to assume, because of the second law of thermodynamics, there is something wrong in the microscopic dynamics. We will assume Newtonian mechanics all the way through, so the micro-reversibility. So we must admit that the sequence D to C to B to A is possible. I can reverse the velocities and that will happen. So that already means that the second law of thermodynamics cannot be the same, cannot have the same validity as, let's say, Newtonian laws. Because there, if I forget about relativity and quantum and so on, they are just whatever initial condition, whatever state, it has to obey. But here I'm giving an exception to the law. Okay, so there is something different flavor, unfortunately, but that's true. There is different flavor of the second law in terms of being every time that has to, so you know the other one cannot happen because delta is negative. Okay, so that's and again, I'm talking now about an isolated chamber. I'm not talking about closed systems. I'm talking about this isolated chamber where there was a spontaneous irreversible expansion. Why there is no spontaneous irreversible compression by reversed velocities? Okay, so the simple answer is yes, indeed, theoretically, the second, the bottom sequence, the reverse sequence can happen, but it's extremely unlikely. And this is where the macro of the system plays a role, important role, crucial role. So if you take 3 billiard balls and you look at them jumping back and forth on the table, and you now look at the, imagine you turn on the, you reverse the velocities and you go backward, these two trajectories are qualitatively the same. This one looks plausible, that one looks plausible, nothing changed. We saw examples of a trajectory and its time reverse trajectory. Both of them look as plausible as the other one. Pendulum or oscillator or planet and so on and so forth. But when you have a macroscopic number of particles, then the top one is highly likely. The bottom one is almost never observed. This is why delta S bigger than 0 is absolutely true for macroscopic system, because the probability of not seeing it is negligible by all accounts. Okay, so why it is so, and what are the consequences, what are the deeper explanation of what's going on? This will be the next lecture after the break. So let's take a 10 minutes break. If there are questions on this before going to break, that's fine. Otherwise, take a coffee or tea or whatever, and we will dwell into it. Okay, question?
חיים, אפשר לשאול שאלה שהיא טיפה צוללת לתוך הפיזיקה, אז לא בטוח שזה יהיה...
הכל זה צולל לתוך הפיזיקה, מה אנחנו עושים עכשיו? נו, בבקשה.
ההנחה של תרמודינמיקה היא שאם אני אתחיל מכל תנאי התחלה, אני אסיים באותו מצב, נכון? במצב D.
כן.
עכשיו, יש משפט במכניקה אנליטית, משפט ליוביל, שאומר שנפח במרחב הפאזה חייב להישמר, הוא לא יכול לגדול.
נכון.
אז כשלקחתי כל תנאי התחלה, בעצם לקחתי את כל מרחב הפאזה האפשרי, וסיימתי עם מצב מסוים שלא משנה כמה נפח הוא תופס במרחב, הוא יותר קטן מכל המרחב הפאזה. זאת אומרת שבצורה צמצמתי את הנפח במרחב הפאזה.
No. Okay, so let me translate the question. The question is, how come in the spontaneous expansion, what, you know, from A to B to C to D, how come the states, all the initial microscopic state that start with the state A will go to D, but on the other hand, we have the theorem which I already mentioned called Liouville theorem, which says that the volume in phase space doesn't change in the dynamics. So the same in phase space, the same volume in the phase space should be preserved. It doesn't shrink, doesn't go, doesn't expand. And here it doesn't seem to obey that. That's a good question. I'll discuss it after the break, and you'll see how it works. But let me also raise another question. If you already talked about analytical mechanics, you probably studied also Poincaré recurrence theorem, analytical mechanics, right? It says every initial condition, right, will come eventually back in a bounded system, will come eventually back to itself or arbitrarily close to itself. Now that's also crazy, because then it means that if I wait sufficiently long, I must have I must have increase in entropy and going back to decrease of entropy, because I have to come back to the same state. Okay, so the answer to that, I won't deal with it later on, but the simple answer to that is that in a macro system, the time for recurrence is exponentially long, more than the future of the universe, the age of the universe, or whatever. So we don't have to worry about it, but it is a legitimate concern. Okay, so both are legitimate concerns. One is what happened to the volume in phase space during the story, and the other one is why you don't see recurrence, the famous Poincare recurrence. Okay, so the recurrence would just lead to not relevant time constants, but the volume, I'll talk about it.
I'll try in English. Maybe I'll change to you.
Okay, good.
I'll see. About the macro-irreversibilities we talked about, about the closed system. I figured, I started at the beginning that you're talking about infinitesimal change, but since you're talking about like all the particles, the idea that all the particles will return to the same exact state is kind of unlikely, I guess. That's what I'm asking.
I didn't understand.
You start with a closed system.
Yeah.
And then you go after, and then you reverse back to the initial state, right? And you say that it's the same.
You're referring to how I go back?
Yeah, and you're saying that it's exactly the same initial condition.
Here.
Yeah, that allegedly all the particles are exactly in the same condition.
Well, no. Well, you have to be careful. Here, when I discussed reversibility by compressing the gas back into this half of the chamber, I'm talking about the macro state coming back, not that the micro state is the same. Not the position of the car.
So that makes sense.
Reversibility means that this is a reversible expansion. It means that you can, by appropriate work, make the macro state go back to the same. It doesn't, absolutely the positions and this completely different. Okay? It just that the macro state is the same. That's what it means by reversible. If you look at the irreversible, the macro state of the world has changed, right? Yeah. Because the macro state of the closed system went back to itself, but the macro state of the world has changed because there was, in other words, if you compress it, because then there will be a net work and then there will be a net heat. So the macro state of the world has changed. Whereas if you will compress it back, but here, the macro state of the world and the container has not changed. It will go back to its initial condition. But it does not mean that the system, the positions or the velocities will have any relation to the original one. Okay?
Yes.
But Elisheva, when I talk here about reversing the microscopic velocities, it's something else. Because if I reverse precisely the velocities in the final state, I'll come back to the compressed state, but not only in the macro sense, but I'll come back to the compressed state where the relevant time, all the positions here will be the same as the positions here, and all the velocities here will be the opposite of the velocities here. Right. So this is now will be kind of a microscopic relationship. But if I just compress it by a macroscopic means, like applying force on it, then there is absolutely no relation between them. So this is why this is weird. This is a kind of what I said is a spontaneous compression because I'm not applying anything. I'm just saying, let's imagine that you will reverse let's imagine you start here with reversed velocities. Then it will go to here. Okay. So I just want to tell you that this difficulty is not something that, you know, we tell a story to the students and so on. This was a major controversy at the time where the thermodynamics laws were formulated, particularly by Boltzmann, and some physicists just denied the validity of the second law of thermodynamics because it violates the micro-reversibility. So this is a major issue. It wasn't just amateurs that had problem with that. And the answer is not universally accepted. But as in other parts of the lectures that we will discuss here on science, I'm giving you, it's not my own theory explanation. I'm giving you the explanation of Boltzmann, and I think that explanation is the makes the most sense. Although there are some other all kinds of stories that I'll mention briefly later on. Okay. So let's move on. Let's move on to. I want to define more precisely what is the relation between a macro state and a micro state. So in the left side, and again, this is something which I want to warn you, that when there is some potential confusion between volume in the three-dimensional container going from small volume to large volume and volume in phase space. Now I'm talking about phase space. So each point, so this is this multi-coordinate. This is r to the 6n, where n is the number of particles in this gas, okay? And in this high-dimensional phase space, every point is a possible microscopic configuration of both location and velocities, right? It's 6n dimensional phase space. So you have to keep it in mind, okay? A point here is a particular microscopic configuration of the particles in the gas, in the container. All right. So now it's a huge, but one thing that we know, and we want to talk about the dynamics here. So one thing which we know is that energy is conserved. Let's talk about isolated system. Okay, energy is conserved. If energy is conserved, then we can take hypersurfaces. Here it's a plane, but it's not a plane. Some surface, the collection, the manifold of all microstates in the phase space that have the same energy. So this will be kind of the manifold E1 correspond to E1, E2, E3, and so on. And now, since we are interested now in the dynamics of the system, of an isolated system, energy is conserved, we don't have to work on the entire phase space, but we just have to work within that manifold. So I'll call it on the right-hand side, I just call it gamma E. Imagine that we start with some energy E. In our case, it will be the total kinetic energy of the particles in the gas. And we take the slice in the phase space that correspond to that energy. So that's it, that this is this square in the right-hand side. And now imagine we have a particular microscopic configuration of the gas, of the molecules in the gas, corresponding to that energy. So this is what I denoted by X. So X is a microstate, okay? And now, let's talk about the macroscopic properties. For instance, what is, okay, number of particles, it's isolated, won't change, but what is the pressure? What is the volume that microstate occupies, etc., etc.? What is the distribution of gas corresponding to that point? Okay, remember my initials. That's a macro variable. The spatial distribution of the molecules in the gas corresponding to one point, one microstate. So we collect all these properties and we get a sub-manifold, which is gamma of X, which is the macro state corresponding to the macro properties of the microstate X. So I want you to understand that the macro state is not a statistical average, it's a property, it's a macroscopic property of a microstate. I can take a microstate and I can compute from this, I can compute how many particles are here, how many particles are here, how many particles at this velocity, how many particles at that velocity, and so on. That is the macrostate, macro properties of the microstate, okay? So gamma of X, so gamma is the macrostate of the particular microstate X. So why this is a submanifold? Because there are many microstates near X which will share the same macroscopic property. This is why I had this oval shading here, gamma of X, because there are many X's which will share the same macro properties as X. Okay? So is it clear? So I imagine I have gamma of E, fine, and then I slice gamma of E to different possible macro properties. So each one of macro variables will give me a subset. Okay, X happens to be in one of them. Okay.
Can I ask a small question?
Yeah.
Should we assume that all microstates that share the same macrostate are in close vicinity to each other, or not necessarily?
I'm assuming smoothness.
Okay.
Yeah, I'm assuming smoothness. There may be some extreme cases where it's not, but I'm assuming smoothness. Yeah. Okay. So look, this is what I'm defining, Liad, the macrostate is at a given time. Okay. So the macro properties are typically like total energy or even the distribution. If you change a little bit the micro state, when it evolves in time, it may go to someplace else. But I'm talking about an instantaneous in time. I'm not talking about equilibrium at all. I'm not taking a snapshot of the microstate of the system at a given time X and computing at that time the macro properties of that state. And macro properties are usually kind of smooth functions of the micro properties. So I imagine that in the neighborhood of X, they will have this manifold is kind of contains state velocity, right? Okay, that's good. That's in one time. Okay, so
I also have a question.
Yes. Yes.
If it's a frozen snapshot, can you
raise your voice and you raise your sound?
Calculate from.
Yeah, go ahead.
Yes, is it good now?
Yeah, okay, very good.
So if it's a frozen snapshot,
yeah,
how can you calculate some like the temperature or something like this, if it's not necessarily in equilibrium?
That's a good question. Okay, not all macro variables apply to non-equilibrium. It is true. Okay, but I said things like pressure, things like density. Particularly, I'm interested in the distribution of velocities and spatial locations that you can define even for non-equilibrium. Your point is well taken. Not all properties have meaning in non-equilibrium. All right. So now we're interested in dynamics. We're interested in what is this irreversible thing. Okay. So here's the dynamics. So let's look at this x0. Let's look at x, an initial microscopic state. And this is residing in some macro state, instantaneous, which I call gamma 0. So basically, in the top left corner, you see what I'm aiming at. I can define now the evolution in time of the macro state by following the macro state occupied by the trajectory of the microstate, right? So here is the initial condition. X0 is occupying a initial macrostate gamma 0, okay? And then after time, I don't know, T1, X0 is mapped by the Newtonian dynamics to another point in the volume space, in phase space, which is X1. X1 belongs to another macrostate, gamma 1, and so on and so forth. And then when it reaches equilibrium, it doesn't mean that X2 it keeps changing, but it reaches gamma 2 and then it goes around and stays in gamma 2 essentially. Okay, so that's why it reaches equilibrium. Okay, as I try to show in this diagram, the point that Boltzmann explains why delta S is bigger than 0, what's going on here, why we prefer the expansion in entropy is very simple, is that the initial non-equilibrium low entropy state correspond in phase space to a very small volume. So gamma 0, the initial macro state, occupies very small volume in phase space. And gamma 2, which is the equilibrium macro state, is much bigger. It's not only much bigger, but it's actually exponentially bigger, as you see in the bottom equation. Omega is the volume in phase space of the equilibrium macro state relative to the initial macro state, and it's exponentially large. So it's so large that most of the volume is essentially occupied by the equilibrium macro state. And therefore, Boltzmann argues, quite plausibly, that almost all microstates in the initial macro state gamma 0 will end up in gamma 2. So, for instance, gamma prime 0, I just chose another initial micro state in the same gamma 0 macro state, okay? It will evolve in a different trajectory, but most likely it will also end up in gamma 2, okay? Just because most of the phase space is there, okay? So this is why we are approaching the high entropy equilibrium rather than something else, because the equilibrium is a macro state, which basically most of the phase space belong to that equilibrium state. Okay, that's step one. And okay, that actually, this explanation gives us already a hint of what is entropy. So if this is what's going on in the irreversible spontaneous evolution into the equilibrium, then if this is the argument about volumes in phase space, then it makes sense that entropy is related to the fractional volume of the macro state in phase space. And because it's extensive, then the log is the right. So up till now, the entropy was related to heat and coming from kind of engineering of engines and going in a reversible process, irreversible process, and so on and so forth. But now we have kind of a microscopic definition of what entropy is, okay? And that brings to the famous Boltzmann entropy, and here at the center of the slide. And I want to emphasize, entropy is again a property of the microstate, like any other macro properties, okay? So the entropy of a state is the log of the volume of the macro state occupied by that state, by that X, okay? Is it clear? So that's the way we can connect the microstate X to the entropy of that state by log of the macrostate, which is in this. And this is why it's now clear that why the entropy increases, because you're just most of the trajectories will just go where the phase space available for them. That's basically the argument. Simple argument. There are some subtleties. When I say most trajectories, how do I count in a continuous or not continuous? What is most? What is the measure? So, you know, for those of you that know what Lebesgue measure is, I would use Lebesgue measure. In other words, I count states here in kind of a uniform measure on X and velocities. But the truth is, it doesn't really matter. Even if I do, even if I define something which is not uniform, as long as it's not terribly pathological, it will never overcome the exponential growth in the volume. E to the n, when n is 10 to the 23, e to the 10 to the 23 is something which is unimaginable in terms of the volumes, okay? So that's the argument. That's Boltzmann's definition of entropy. There is no consensus about that, but okay. And again, it's nice because what I like about it, it's not only this log of number of states, but it is a property of each of the microstates belonging to that macrostate. You can attach entropy to the microstate. Okay, and the top of this, I bring something that I don't know if it is a historical fact, but there are rumors that von Neumann told Shannon when he came up with the information theory, he didn't know how to call it Shannon information, and von Neumann told him call it entropy because nobody knows what entropy anyway is, so you'll have an edge. Okay, anyway, so Boltzmann gives us final entropy. Okay. So by this definition of entropy, by relating entropy to the volume in phase space, it gives a natural explanation of why entropy tends to grow. Okay, but that's not the end of it. And Boltzmann himself knew that it's not the end of it. And this is why. Okay, we have to now look at this story, and again, x0, x1, x2, and now we have this gamma 0 to enormous, to increasing, exponentially increasing volumes in phase space, gamma 1 and gamma 2. And again, I want just to explain to you in the context of the gas. Gamma 0 will be all the macro state where all the particles are in the first half after you left the partition at the initial snapshot. And gamma 2 when it's filled in the entire gas. But this is in real space. Here we're talking about phase space. Okay. But I can now ask the following question. Suppose I take x2 here at some point in time where it's already in the kind of equilibrium macro state and reverse all the velocities. So I go from x2 here to x prime 2. Why I'm going from here to here? Now the prime has different meanings, so don't confuse me. I'm now using the same graph, but having a different meaning to x prime. Here just was another choice. Here it's not another choice. It's a specific choice. I take x2. Remember, x is both position and velocities, and I reverse the velocities. So then let's say this is now I get this reverse state, velocity reverse state, which is still in gamma 2, because it's still, the gas is uniform. Even if the molecular velocity is reversed, the equilibrium properties are the same, okay? But now I know from time reversal symmetry that it will evolve back into gamma 0. So what's going on? We're still in the puzzle, right? Okay. So the answer, so what is the situation? The situation, and that's going back to what, where is he? Avishai or Yishai? We lost him. Are you still here, Avishai?
It was me, I asked the question.
Sorry, Avidan. Okay, that's going back to this question. Let's understand better what's going on in gamma 2, in this equilibrium state, where all the gas are kind of uniformly filling the chamber. Okay, so here's x0 to x2. Okay, here is the time reversed, the green one. Okay, what happens if I take x2, and that's related also to question of Liad. If I take x2 and make a small change in the location or in the velocities, and similarly, or for, you know, I can do it in x prime too. I can, you know, change a little bit. Then I get this y trajectory, which is just circling around and wandering around in gamma 2. So gamma 2 has exponentially most microstate where the trajectories are just keeping going around and around in gamma 2. That's most of the states in gamma 2 are these trajectories. Then there is a very exponentially small states in microstates in gamma 2, which came from this, like x2. And again, there are exponentially small states in gamma 2, which are doing the reverse. This is what gamma 2 is. So Jonathan asked about Liouville theorem. There is no problem, because all the microstates in gamma 0, all of them evolve into gamma 2, but they occupy a very small volume in gamma 2. Actually, they occupy only gamma 0 volume in gamma 2. They are very unlikely states in gamma 2. And so are the reverse. Let's go back, okay? Most of the equilibrium states are states that will not go, didn't come from low entropy state and don't go into low entropy state, that that's keeping in the high entropy state forever. Okay, that's the picture. You understand? You're with me? Okay, good. So now here's the question. A, B, C, D. Okay. So when we see this, we say, okay, so you know there is some expansion, spontaneous expansion of the gas. Okay, but if the reverse the final velocity will go backward, as we said. Okay, so here's the question. What I'm claiming now, that both stories are unlikely. Previously, I said, well, you know, that's what you expect, and here you don't expect that. I'm saying both of them I don't expect, because both of these, I'm looking now at the state here at the present in equilibrium in gamma 2. What is the chance that this state evolved from low entropy? Exponentially small chance. What is the chance that this state will evolve into low entropy? Also exponentially small, the same exponential. So if I see a gas filling a chamber and I ask what's going on, I say, well, of course, this is just a state which is equilibrium from the beginning of Bereshit. To assume that the future of the state will go to low entropy, which is the bottom sequence, is as unlikely as to assume that it came from low entropy state, because low entropy state is low entropy state, is highly unlikely. Okay, so this is basically the question. Why now the question is the opposite. Why we are seeing, why we believe that A, B, C, D rather than D, C, B, A, both of them are unlikely. Either the future is low entropy or the past is low entropy. Actually, if I see the chamber, what I will say, that there is some fluctuation in the equilibrium macro state. Now, if you tell me, look, Haim, if you tell me the following, you tell me, I know that this state here have the particular here. I know that it has this bizarre state with velocities which have some particular shape that tend to move forward and so on from right to left. I'd say this is fluctuations in the equilibrium state. Fluctuation. It so happens that you have this rare state. I wouldn't say that it's a state which came from low entropy. So basically, the point is that both of these scenarios are equally unlikely. Most likely, what happens is that you have an equilibrium state which was forever was in equilibrium and stay in equilibrium, and that's what the most typical things will happen.
אני יכולה לשאול שאלה?
כן.
אני מרגישה שאתה מנסח את הבעיה לא בצורה אמיתית, כי אתה כאילו מנסח את השאלה בצורה שהיא מוטה לכך שהאנטרופיה יכולה לקטון באותה סבירות כמו שהיא יכולה לגדול, אבל אם אני נגיד רואה גלידה נמסה, אז אני יכולה לדעת בוודאות שהיא הייתה לפני זה במצב מוצק או משהו כזה, ואני יכולה לדעת בוודאות שהיא כנראה לא תחזור למצב מוצק.
אבל זה בדיוק השאלה, הנה, אני אראה לך דוגמה.
אז אני יודעת שהעתיד כאילו יהיה בו יותר...
אבל זה בדיוק השאלה, אנחנו רוצים להבין למה. אבל בדיוק, בוא נניח, let's take an example, not of the final state. Let's say I am now in state B. You show me a snapshot in state B, which is non-equilibrium, obviously. I know that's non-equilibrium, there is no partition. But I do see that the gas density is not uniform. It feels more, more the right side than the left side. And you ask me what is going to happen? What's going on here? Okay, now it's non-equilibrium, state B. And now you're asking me, tell me, Haim, what's going on here? So, three explanations. One explanation is, well, it started from a compressed gas and somebody lifted the partition, it's on the way to the equilibrium. Just wait, okay? It's one. Another explanation, no, it started from the equilibrium with this reversed things and is on its way to be spontaneously compressed. I'm claiming both of them are highly unlikely. What is the third explanation? The third explanation is that we are in equilibrium, and in equilibrium there are some fluctuations, there are some rare states in equilibrium which happen to be this. We're not lucky. In other words, it's not a trajectory going to here or trajectory going to here, it's just the fluctuations which there is no logic to it. Just happens to be so. Maybe it started with high entropy and to low entropy. Okay. What I'm claiming that the story, if I see half filled chamber, and I'm saying, well, it's on its way to be equilibrium and fully, is as unlikely as the story that it goes back. Why? Because if I am saying in the half filled chamber, not in the half filled, in C, 3/4 filled chamber, if I'm saying, well, it came from a half filled chamber, I'm assuming a very low state, low entropy state, much lower than the present. If I'm saying, well, you know what C happens? C happens because there was a hole in the partition in A is a very low entropy state, okay? So either I'm assuming low entropy state in the past, or I'm assuming low entropy state in the future. Both of them are unlikely. So I'll come to your ice cream. And this is precisely the problem. And by the way, Boltzmann, because he realized that, he said the second law can never be proved mathematically by means of the equations of dynamics alone. Because you can argue that low entropy is unlikely state compared to high entropy, we can understand that, but there is no reason to assume that low entropy in the past is more likely scenario than low entropy in the future. Here we are lost. Why? Okay, so this is basically, okay. So I'll come to you, or soon I'll come to you ice cream, although it's not an ice cream, but the omelet, but soon will be. Okay, so basically here's what Boltzmann said. He didn't understand why, but he speculated the following. And this is what's called the past hypothesis. The past hypothesis is the following. Suppose again, I'm looking at C and I'm saying, well, I know what happens. It started with a chamber, and then, you know, somebody compressed the gas into a chamber and then lift the partition and so on and so forth. Why this is something which is plausible? Because I know how to do it. I know that's what you do. You know, you compress a gas and you put a partition, you remove it. It's a plausible scenario. I don't have a plausible scenario from this, for this one. Because for this one, I don't have a means to generate this low entropy in the future, because that would require some fine tuning of the of changing the velocities in this high entropy state, and I don't know how to do it. I know how to compress a gas. So assuming low entropy state in the past is legitimate because I know how to create it. I know you can compress a gas and it's a low entropy, fine, and then release it and then do this. I know it's a low entropy state, but I know how to create this low entropy state by physical means. This macroscopic means I cannot figure out how to create an initial condition which will reverse those micro velocities and generate low entropy in the future. That's the argument. The past hypothesis means that although I'm assuming low entropy in the past, the reason why this is legitimate because I know how to create low entropy states in the past. It's somewhat like the electromagnetic story with retarded and bands. I don't have time, but you can see that it has to do with the same story. Okay, good. So now, okay, so here's the omelet story. So imagine I see an omelet, okay, in the pan, okay? So, well, what will I say? Well, the plausible scenario is that it started from eggs, and then it was scrambled, and then, you know, they turned into scrambled egg, okay? Well, but this story is insane, because to assume that there was an egg in the initial state is to assume a very low entropy state. An egg is a very low entropy state compared to a scrambled egg. You have to really put all the molecules inside this confined shape. It's a very structured, very ordered state. So an egg is an extremely low entropy state compared to the scrambled egg, okay? I could maybe say, no, come on, the scrambled egg is on its way to spontaneously go into becoming an egg. Okay, this is your ice cream question. This is, why not? Here I'm assuming low entropy in the past, and here I'm assuming low entropy in the future. They're equally unlikely from the point of view of volume and phase space. Well, I could also assume that, you know, I had a scrambled egg from the Big Bang time, and then a scrambled egg, and that's it. This is the most likely, in terms of volume and phase space, most likely is that I have a scrambled egg. That's one of the states in the trajectories going around and around in the equilibrium state. Okay, but we do favor the top one. Why? Because we have a plausible story. We know how to create from low entropy, how to create this low, not to create, but we know that we have in the world the low entropy states, which are eggs. And we have humans that know how to break them and scramble. and put it on the pan and so on. Humans are very low entropy structures, and eggs are very low entropy. So it is a very low entropy state, but we know it exists. Okay, so this is plausible, and the other one is not. Okay, so, but we have to go further. Okay, so we came to an egg, and now we said an egg is a low entropy state compared to the scrambled egg. Oh, fine. And we say it's plausible because we know that there are eggs around. But how come there are eggs around? How come we have in the universe such a low entropy state, which is an egg? Well, we know an egg was laid by a hen. Okay? So the hen is even lower entropy state than egg because there are many other ways to create an egg. In our world, it is by hand. So here we have the hen. It's even lower entropy state, but it's fine because we know that there are hens in the world. Okay, how come we have hens, chickens? Well, DNA. DNA is even lower entropy because there are many DNA's configurations that will give rise to the same hen. Okay. But a specific DNA is much lower entropy. And you can see, you know, how come we have DNA in the world? Well, we have primordial atmosphere in the universe, on Earth. It's a very, again, it's much lower entropy than a DNA because there are many configurations of the of plausible scenarios that give DNA rather than that one. But that one we learned in.
But you're basically saying that the chicken necessarily came before the egg because it has lower entropy?
What I'm saying is that the way we explain a low entropy existence of low entropy state is by a story involving even lower entropy. So basically we say, look, we have hen. It's a low entropy state. Okay, but eggs, again, not mathematically, eggs evolve from, generated dynamically from a hen, but egg is a higher entropy. Why it's high entropy? Because the same egg can be generated, conceived by many other things or many other configurations or whatever. I'm just making it up, but you understand what I mean. We are always telling a story relying on, because you see, if the hen was high entropy, well, then it will be a remarkable violation of the second law of thermodynamics. You go from high entropy to low entropy here, but it's not true. A hen is a lower entropy than egg because it has more structure and much more much more fine-tuning macroscopically than an egg, and so on.
Find the lower entropy by bigger number of structure?
Higher, no, because a hen it has more molecules, but it has more structure. You have to specify more macroscopic constraints. Let's say an egg is part of a hen, just to say, okay, so now a hen, you have it's a bigger object, but it's not just a gas of molecules. It is, you have to design a hen to build to generate an egg. So you have to constrain not only the egg, but also the mechanism that generated the egg in a very specific way, and so on and so forth. So you can see that very quickly you go to the Big Bang or to the initial state of the cosmos. And you say, if this story makes sense, then it means that the initial condition of the universe is a very low entropy. And that Boltzmann, it's amazing how genius he was. He didn't know anything about cosmology at that time. Nothing, Big Bang, nothing about cosmology, galaxies, and all this stuff. But he figured out that the only way to save the second law of thermodynamics, make sense of it, is to assume that our universe started with an extremely low entropy state. Now, you see my words, you would imagine they don't make sense because the universe started with some state, a microstate, and I attach it an entropy. But remember, an entropy can be attached to a microstate. In other words, our universe started from a specific microstate, but which belongs to a very low entropy macrostate. That's the argument. If you buy it, then the rest is fine. Then now the universe is irreversibly expanding and entropy is increasing. And therefore, we are telling this story rather than the reverse story. There are humans, there are hands, there are pistons, there are pumps, and so on and so forth. So imagine, and I don't want to get into this philosophy, what happens if the universe would start with high entropy and do a big crunch or something? Maybe everything will, I don't want to get into it, but that's a statement. The universe must have started from extremely low entropy state. And this is why we see all the time processes which increase, spontaneous processes, which increase entropy rather than processes which decrease entropy, because it's part of the increasing in the entropy of the universe. Okay, it's amazing, amazing argument. Okay, so I'm sorry. Let me give it a two. So let me just give two minutes. How come? What does it mean that the universe started from a low entropy state? Here is the picture on the right, top right. This is a rendition of the distribution of background radiation, microwave radiation, a relic of the Big Bang. And there are some fluctuations here, but actually it's an amazingly uniform. And it's basically.
Haim, are you showing something? Because I don't see it in the slides.
The last one.
Okay.
The last one is it's an image of the sky. And the color is the fluctuations in the microwave background radiation of 3 Kelvin, okay? But at some scale, the universe, the early universe, this is now today, so to speak, but the early universe was very small and extremely uniform, spatially uniform. This is evidence, but so many observations that it's rock solid. The early universe started with an extremely small, spatially small entity, but with an extremely uniform distribution of matter and photon and energy and so on. So now I'm asking you, is this a low entropy or this is high entropy? There's a paradox here. On one hand side, I say the second law of thermodynamics makes sense only if the initial condition of the universe was a very low entropy. On the other hand, I'm telling you that all evidence is that the initial condition of the universe was extremely uniform spatially. You remember how uniform gas were uniformly filling the chamber. So why I'm saying this is low entropy? This should be high entropy, right? It is. You understand the question? Shane, okay? You understand the question? What is the logic of the claim that the initial state of the universe is extremely low entropy, where actually it is very uniform, filling the space, matter and energy and photon. Okay, that's the question. Oh, here's the answer. One word. Okay, here's the answer. When we are talking about ordinary matter, like gas and so on, they are dominated by short-range forces. Okay, then uniform is the state, the equilibrium state with the highest entropy. However, When you are talking about the universe, the scale of the cosmos, we are talking about matter dominated by gravity. Gravity is long range and gravity is attractive. So what happens when you have particles which are attracted over a long range scale? Well, they tend to collapse. They tend to cluster, to form galaxies, stars, and so on, by gravity, by the force of gravity. So actually, what's going on here? The answer is the following. Under gravity, when we talk about uniformity, we have to think about phase space. In gravity, high entropy would be matter collapses, okay? The spatial part of the phase space is very low entropy potentially because it's constrained to occupy very small region in 3D space. So it's a very low entropy, but there is a velocity sector. By collapsing matter, gaining energy from the interaction, you can go to extremely high velocities. And this is what increases the entropy, because the entropy wants to be uniform in velocity space also. It turns out that this dominates. So matter dominated by gravity, the irreversible, natural irreversible process or high entropy state will be collapsed, clustered, and having non-uniform structure in space, in real physical space, but a more uniform, unbounded structure in velocity sector. And the total entropy is much higher, okay? And this is my last slide. This is speculation by Penrose and some others. You can take it just, you know, with a grain of salt, but you can do the calculation, the following. You can estimate the entropy of the observed early universe, the actual universe, okay? The number of particles, number of baryons, and so on. And you find that the entropy is 10 to the 88, basically more or less the number of baryons in the early universe, okay? Now you can ask what happened if all those baryons, all this matter, all these particles would start with the black hole. The entropy would be 10 to the 121. If you take into account Bekenstein-Hawking's famous formula for the entropy of black hole. So a universe starting in a black hole is the highest entropy. And a universe like us that started from a very spatially uniform particles despite gravity is orders of magnitude in entropy. And imagine in volume is e to that. Okay, so the differences of 3 orders of magnitude in entropy in terms of volume of phase space is amazing. So this is why it makes sense, even if these numbers, I mean, people argue about these numbers and nobody knows actually how to take care of it. There's quantum gravity and all kinds of things. But anyway, I think that the physical intuition is this, that when you have that our matter, which is ordinary, you don't get energy, you don't get internal energy by pressing it. So this is why the velocities are not going to be, you're not going to gain by spontaneously collapsing it. So the uniformity in space is what is dominating, and it makes high entropy is uniform distribution in real space. But in matter dominated by gravity, like the early universe, the high entropy is actually everything to be collapsing in black holes and so on. And the fact that the universe did not start like that, obviously, it started like uniform, is an amazing fortune, is amazing luck, is amazing mystery. It's amazing miracle that we have to explain. But the only explanation is that if it started as a black hole, we won't be here to question, to raise this question. But anyway, this is philosophy. Whatever the reason is, we can say empirical evidence and is that the early universe started with a very low entropy state, and the entropy of the universe keeps increasing, like the second law. And this is why we have partially low entropy entities in our world, like animals, like fruits, like life, and so on and so forth. And this is why the scenario of low entropy states in the past makes more sense given this context than a scenario of having low entropy states in the future. Okay, next week, probabilities. We turn this intuition into probabilities, statistical mechanics, statistical dynamics, and the brain. All right, good. Question on this. It's an amazing story, I must say. It's like unbelievable story to explain the second law of thermodynamics, the universality of it, by really forcing you to go back larger in space. You know, if we want to explain the chamber, the expanding chamber, you don't have to assume anything about cosmology and black holes. You can assume, well, you know, the humans and the machines that compress and so on. That's good enough. We know how to create low entropy. But if you further ask, okay, how this came into being and so on, if you expand the horizon of your question, you end up asking a question about the initial state of the universe.
Sorry, could you explain again the different macro states and how you come from a smaller macro state to a more broader macro state? And there was a slide about earlier, I think, about the gamma. I think yes, here exactly.
Yeah.
Yes. The change of the macro states, like you still. So the point is that the gamma. What's the difference in like in gamma 0, gamma 1, gamma 2, and what's the progression line? I understand that like intuitively it's very much understandable that obviously we have a gamma 2 is you can't reverse it somehow to gamma 0, but why is it so?
Well, because okay, so x0. So before we're talking about dynamics, we can, as I said, we can slice the phase space into different macro states, gamma 0, gamma 1, gamma 2, and so on. And they will have different volumes, and the ratio between their volumes are really exponential, right? Okay, so again, I'm discretizing. So you have gamma 0, a small volume with a macro state like all the particles and one part of the gas. This will be gamma 0. And then gamma 1 is like 3/4 of the gas filling, so more smoother density, particle density, but still not. And gamma 2 is like uniform. So these are states which exist without worrying about dynamics. But now, because they have such a bigger volume in phase space, if I take a typical microstate gamma 0 in this low entropy, and I ask where it is going to end up or where it's going to evolve, it will be most likely evolve into a microstate belonging to a larger volume than to, let's say, remain in gamma 0. So you might have rare state in gamma 0 would just remain in gamma 0. But it's extremely small number of those states. Or that it evolved into another state, which is, you know, some small. So what I'm saying is that the microstate, the typical state or the vast majority of initial state in gamma zero will evolve into microstates at time t1, which is largest volume available to them at that time. That's what I'm saying. And similarly, from gamma 1 to gamma 2.
So just to have a good understanding of this, like because of the particles in gamma zero are making, let's say, some choices, whatever, just for the sake of the argument, choices, and then they have more choices to go through. That's because you have an exponential growth of the choices, and going back to choices would be just highly unlikely. So the more choices basically the particle knows where to go, the more choices they'll have in the future, because the choice space expands from gamma 0 to gamma 1, gamma 2, because the volume expands.
Right, but again, I'm saying the trajectory is still unique. For each microstate, the trajectory is unique. Okay, so we're not taking one trajectory and expand it. It's for each microstate starting from gamma 0, there is a unique trajectory. But the question is where this trajectory is landing at time t1 or time t2. And I'm saying for a trajectory, for initial condition x0, to stay in gamma 0, there are states like that. But this is extremely fine-tuned initial state to make it stay in gamma 0. You really have to make all the velocities such that they don't use the fact that there is no partition, right? If you take a typical state where you have velocities which were confined and now you leave the partition, they will have net flux into the right, and therefore they'll evolve into gamma 1 and gamma 2 and so on. But it's not that one, I mean, the choices sound like one microstate makes choices. It's not about that. A microstate has a deterministic trajectory. It's just an argument why a typical microstate will go into a state that is occupied by gamma 1 and eventually by gamma 2. Because to avoid gamma 2, you will have to design a very specific initial condition. That's what I'm saying.
Okay, thank you. That was a good addition. That the
right? There are states in gamma 0 which don't do that, but that, I mean, to make them avoid this huge volume in phase space, you will have to make sure that the velocity is always going, in the left rather than in the right. You will have to really make a fine-tuned choice. The typical state, which is, typical velocities and typical position and so on of the particles, will necessarily, go into that high volume in phase space.
Another philosophical argument, which I wanted, according to the last slide, about where there's that we're coming to a more, let's say, we have more and more entropy into the world as time progresses.
Yeah.
But if let's look at, for example, our planet. Like if we just look at our planet, we as human beings made tons of low entropy structures, and we were ourselves multiplied. Therefore, we also contributed. So you say if you look at we don't have to look at the universe, because I think everything that happens on the planet is pretty much closed universe, more or less. I don't know, maybe you'll contradict that. So you think climate change will just make up the entropy which we just made here on the Earth?
Yes. So let me give an example. And again, we can discuss more detailed biology and so on, but let's give an example. Is the photosynthesis, or right? So life on Earth relies heavily on photons from the sun. Okay.
And because it's not a closed system and the energy.
No, but okay, so I'll come to that. So now you can ask yourself what's going on about the budget when the sun radiates photons in Earth, and it's being used by life and organic material and so on. What is going on here? So naively you would say, well, the Earth absorbs energy, electromagnetic energy, and you know there is a loss of energy, it becomes heat and so on. The truth is not. The truth is that there is very little energy absorption by Earth, electromagnetic absorption from the sun. Most of the energy is actually reflected, not absorbed, reflected back into into space by electromagnetic radiation. Okay, so basically, what's going on here? What is life? What is organic material and so on? The answer is, what the Earth gains is entropy. Earth consumes entropy from the sun, not energy. Why it is so? Because the sun radiates photons with high frequencies. Okay, so if you know high frequency, the total energy will be, if it's high frequency, then each photon has high energy. So the number of photons that make up a total energy is relatively small because each photon has high energy. The Earth radiates in infrared or low frequency radiation. Low frequency radiation means that the same energy is now distributed over many more photons. It's higher entropy. Okay, so what happens is that there is a low entropy radiation converted into high entropy, and the difference in entropy is partially consumed by generating you and me and planet, not fully consumed. The total budget of entropy still increases, but life and organic material and so on is able to use part of that entropy to use low entropy structures like us, partially. So it's interesting. It's there are studies about more specific things than that about organic and biology in general. But that's a general story. The general story is that the total energy of the universe is increasing, but we and creatures and trees and everything, life on Earth is able to convert entropy from the sun primarily into low entropy structures, and while the total entropy still increases. So that's more or less the story. Of course, the details we don't know. We don't know, how life started and so on and so forth. But this is, I think, in broad line, this is the story. We are able to locally use up some of the entropy into generating low entropy structures, and then compensating, of course, by increasing the entropy of the surrounding. So while structures like us and life on Earth grows, so it's compensated by emitting into space high energy photons. So altogether, the net change in entropy is increased. Okay, interesting story. It's, I think really something to think about and to read more and so on.